This lecture is about the basics of parameterized complexity. We're going to revisit what we have done for vertex cover, talk about problems that probably do not have FPT algorithms, and then we're going to see how different parameterizations of the same problem will affect the parameterized complexity of the problem. Okay, so we all remember what the vertex cover problem was. So in the input we had the graph G and an integer k. K is our parameter. And the question is whether there are k vertices in the graph that together cover all the edges of the graph. So the vertex cover problem can be solved by brute force in either 2 to the n time or n to the k time. Depending on whether we enumerate all subsets of the vertex set or just subsets of size k. There's a simple algorithm that solves it in time 2 to the power k, a slightly more advanced algorithm that solves it in time 1.4656 to the power k, and I always ignore polynomial factors here by using the O star notation. Chen, Kan, and Jia showed an algorithm that does some preprocessing. So in time order k plus n, it computes a kernel, and then it solves the kernel in exponential time in k, so in time 1.2738 to the power k. So what does that mean in practice? So if we have 1,000 vertices and our parameter k is 20, let's look at how many instructions we need to execute and what this means for real-world running times. So the 2 to the power n time algorithm and the n to the power k algorithm are hopeless. So they would need more than 10 to the 41 years. We get very competitive running times when we have our first FPT algorithm that has running time 2 to the k times n. And so the real world running time drops and drops with faster exponential time algorithms. So when we get better dependencies on this function k that determines our running time. So here we assume that 2 to the 36 instructions are carried out per second. And one notice that the Big Bang happened roughly 13.5 times 10 to the 9 years ago. So the goal of parameterized complexity is really to confine the combinatorial blow-up of the running time, of the worst case running time, to the parameter k. So we will allow the running time to depend exponentially only on k, and everything else is polynomial. So the question is now, if we have a problem and a parameter, is it fixed parameter tractable or not? So can we find such an algorithm with running time f of k times a polynomial in n? So, or in other words, for which problem parameter combinations can we find such algorithms? And then once we have such an algorithm, the second question is, how small can we make the f of k? We could add a third objective here. That means that is how small can we make the kernel. So we know that every problem that has an FPT algorithm also has a kernel. So we could also ask how effective can we make the preprocessing. So now for a parameterized problem, we always specify what an instance is, so what the input of the problem is, what the parameter is, and then there's a yes-no question about the instance and the parameter. Parameter can be various things. So it can be the solution size, it can be the input size. That would be a trivial parameterization because if the input size is our parameter, then every decidable problem that's parameterized in this way is fixed parameter tractable. But then there's still the question of making this f of k smaller and smaller. it could be, so the parameter could be related to the structure of the input. It could, for example, be the maximum degree of the graph, or other parameters of the graph parameters, such as tree widths, branch widths, genus, etc. Or it could be a combination of parameters. So our parameter could be the size of the solution plus the largest degree in the graph, for example. So it's anything really that's related to the input or the solution that we want to find. Okay, let's talk about the coloring problem. So here we have as input a graph G and an integer k, and the question whether G has a k coloring, and we look at the parameter k. And the k coloring is of course an assignment of one color to each vertex, such that no two vertices receive the same color if they are adjacent. So brute force algorithm would solve the problem in time O star of k to the power n, because for each vertex we have k colors at our disposal. So if we try all those possible k colorings or assignments of k colors to the n vertices, we get order k to the n possibilities. Björklund, Husfeld, and Koivisto designed an algorithm for coloring that has running time 2 to the power n, and this is done by inclusion-exclusion. But is this problem fixed parameter tractable? So these two algorithms I mentioned here, they are not FPT algorithms because you can see that the exponential function depends on n. So in our O star notation, we still have an n that's lurking there. But we know, of course, that coloring is NP-complete when k is equal to 3. So suppose there was an FPT algorithm for coloring, then 3 coloring could be solved in polynomial time, because O star of f of 3 is the same as O star of 1, so and that's a polynomial. And therefore p would be equal to NP, so coloring is not fixed parameter tractable unless p equals NP. Okay, let's consider the clique problem. So a clique in a graph is a subset of vertices such that every two vertices are adjacent in the graph. In the clique problem, the input is a graph G and an integer k. K is our parameter, and the question is whether G has a clique of size k. So in this example graph here, we have these three vertices that are all pairwise adjacent, so they form a clique of size 3. So when k is a fixed constant, then this problem is not NP complete, because for any fixed constant k, we can check whether there are k vertices in the graph that form a clique. So we have this n to the k algorithm. Let's write it as n choose k. So you can choose any k vertices among n vertices, and n choose k, that's order n to the power k. So there's this many possibilities that we explore, and to choose k vertices among our n vertices. And then checking whether a vertex set is a clique, that's clearly polynomial time solvable. But now if k happens to be a fixed constant, then n to the power k is polynomial. So the same reasoning we had for coloring here does not work, because for coloring we had that coloring is NP complete when k equals 3. Clique is polynomial time solvable when k equals 3, or any constant. So we cannot rule out that clique is FPT by the same reasoning as for coloring. So could it be actually that clique is clique is FPT? So over the years, people have tried, and nobody has managed to get the FPT algorithm for clique. So what else is there? So we do not currently know an FPT algorithm for clique, but this is where W1 hardness comes into play. So we will see in the lecture of W1 hardness that there are these problems that are hard for one of these W classes, so the intractability classes in the parameterized world, and therefore we believe that clique is not FPT. Next, let us look at a different parameter for clique. So we have the same problem. The only difference is now the parameter. So the parameter is the largest degree of a vertex in G. So this delta of G is the maximum degree of the graph G. So the question is now whether delta clique is fixed parameter tractable. So let's reason a little bit. So we have that the largest degree in the graph is bounded by the parameter. So this means now that any given vertex cannot have very large degree. So, but how does our solution look like? So our solution, let's hook it onto one vertex. So let's say we have one vertex that we assume is in the solution. So how does our clique look like? Well, if we look at this vertex and its neighbors, so we assume that this vertex V here is in the solution, is in the clique that we want to find, then how does the clique look like? Well, it will contain V and some of its neighbors. But it cannot contain any vertex that's not the neighbor of V, right? So if we have other vertices in the graph that are farther away, then this clique cannot contain those vertices. And this is the basis of this algorithm. So the algorithm has as input a graph G and an integer k. It outputs yes if G has a clique of size k and no otherwise. So the algorithm has two holding rules. The first one is k equals 0. So then we just need to check whether there exists a clique of size 0 in the graph, and the clique of size 0 is just an empty set. So we can immediately return yes. Otherwise, so if k is more than the largest degree plus 1, then I claim that we can return no. Why is that? So if we have a yes instance, then there exists a clique of size k in the graph. So in a clique of size k, notice that every vertex is adjacent to all the other k minus 1 vertices of this clique. So every vertex will have degree at least k minus 1. But now if k is too large, if k is larger than the largest degree plus 1, then such vertices do not exist, and that's why there's no clique of size k. If none of these halting rules applies, then we continue, and we just observe first that a clique of size k contains at least one vertex v. Well, this is because k is more than 0. Now, what we will do is that for each vertex, we will check whether there's a clique of size k that contains this vertex. And in that case, the clique must be a subset of the closed neighborhood of this vertex. Now, what will the algorithm do? It will go through each vertex v in the graph and now check for each subset S of the closed neighborhood of this vertex with the size of S being equal to k, check whether S is a clique in the graph. And if so, we return yes. If none of these checks reveal that there was a clique, such a clique S in the graph, then we return no. So for each vertex, we'll just check each local neighborhood and check whether there's a clique that contains this vertex. And if none of these checks succeeds, then we can return no. Okay, so what's the running time here? So the halting rules can be checked clearly in polynomial time. Now we go through all vertices, so that's a factor n in our running time. Now for each subset of the closed neighborhood of V with the subset having size k, we do something. Okay, so now every closed neighborhood has size at most delta plus 1, so delta of g plus 1. And we go through all subsets of size k. So the number of such choices is delta plus 1, choose k. So this is order delta plus 1 to the power k. Okay, we know that k is at most delta g plus 1. So this is order delta plus 1 to the power delta plus 1. Okay, so our running time so far is n times delta plus 1 to the power delta plus 1. Next, we just check whether S is a clique, and this can be done quickly, so that's clearly polynomial. So the running time will be maybe k squared. We check for every pair of vertices whether there's such an edge in G. So this is order k squared. Okay, so in total we have something like n times delta plus 1 to the power delta plus 1 times k squared. So the only exponential dependency here is now on delta, and we conclude that our running time is exponential only in delta. So indeed we get a FPT algorithm with parameter delta. Okay, let's revisit the basic definitions of parameterized complexity. So if n is our instance size and k is our parameter, then of course P is the class of problems that can be solved in polynomial time. FPT is the class of parameterized problems that can be solved in time f of k times a polynomial in n. Now XP is the class of parameterized problems that can be solved in time f of k times n to the power g of k. So those are those problems where we say they are polynomial when k is a constant. But the good classes here are P and FPT. And we know that if FPT were equal to W1, then the exponential time hypothesis would fail. This means that 3 satisfiability would then have an algorithm that solves it in 2 to the power little o of n time. So in sub-exponential time, where n is the number of variables. And then there's just a note that says that we assume that f is computable and non-decreasing. Okay, so there's some further reading on the topic. You can see more about an introduction to the parameterized complexity in several of the textbooks, and here are the references.